Good day to each and everyone. Our topic today report is about multi-lane highways. What are multi-lane highways? So multi-lane highways is vehicles can interleave at a grade intersection and driveways and not full access control. May or may not be divided by a barrier or median, unlike freeways which are always divided. Traffic signals can be present. Design standard can be lower than freeways. Visual settings and development often more distracting to drivers. So, ang multi-lane highways are wide roads designed to handle a large number of vehicles traveling in both directions. These highways have two or more lanes for each direction, allowing faster and smoother traffic flow. They are usually built to connect cities or regions, helping people travel long distance more safely and efficiently. The lanes are often separated by a median or barrier to prevent head-on collision, and each line has marking to guide drivers. Multi-lane highways also include features like road signs, shoulder and sometimes service roads for local access. Overall, their main purpose is to reduce congestion, improve safety, and make travel quicker for all kinds of vehicles. So, next is defining features. In multi-lanes, they have lines, usually for 4 or 6 lines, both direction combined, and speed limit posted between 40 and 60 miles per hour, and medians can have physical medians, two-way left turn lines, or be undivided. And the capacity analysis is level of services or LOS determination closely mirrors freeway procedures with specific adjustment. So the defining feature of multi-lane highways is include several key characteristics that make them different from regular roads. First, they have 2 or more lanes in each direction, allowing many vehicles to travel side by side. And second, the lanes are separated by a median or divided, which help prevent accident between vehicles moving in opposite direction. And the third is multi-lane highways are designed with smooth and wider pavement to support high-speed travel. They also have road marking and traffic sign too. So guides the driver safely, and they are shouldered on the side for emergency and limited access points like ramps or interchange instead of regular intersection. These features work together to make driving faster, safer, and more organized on multi-lane highways. So the next one is assessing highway performance. The primary determinant traffic density is the main factor for LOS. The criteria is based on traffic density, speed, volume, to capacity ratio, and maximum flow rates. Validity condition is procedure is valid for segment without significant influence from closely spaced traffic signals, typically less than 2 mil apart, and significant on-street parking or bus stops, and high pedestrian activity. So, assessing highway performance means evaluating how well highway serves its purpose of safely and efficiently moving vehicles. Engineers and planners study different factors to measure its performance. One major factor is the traffic flow, which look at how smoothly vehicles move and whether congestion occur. And another is speed, which check if drivers can travel at the safe and consistent speed without frequent stop. And capacity is also important. It measures how many vehicles the highway can be handled at the time. Other factors include safely by analyzing the number of accidents and road condition, which examines the quality of the pavement, and marketing by assessing this aspect. Engineers can identify problems like bottleneck, poor road, and design make improvement to ensure the highway remains efficiently safe and comfortable for drivers. So the next reporters will be discussed.
So, these two figures explain the level of service or LOS for multi-lane highways. First, let's talk about the table 6.9. This table shows the loss criteria from A to E. Loss A represents a free flow conditions, meaning vehicles can move smoothly with very little delay. As we move from LOSB to E, traffic becomes heavier, the speed decreases, and the road gets more congested. The table also shows that these values change depending on the free flow speed, or FFS. For example, 60, 55, 50, or 45 miles per hour. When the FFS is lower, the maximum flow rate and average speed also become lower. So basically, the higher the FFS, the better the traffic conditions and the faster the flow. Now for the figure 6.4, this shows the speed flow curves. It illustrates the relationship between the speed of vehicles and the flow rate. At low flow rates, meaning kaunti lang ang sasakyan, the speed is high, but as more vehicles enter the road and the flow rate increases, the speed starts to drop. You can also see the different LOS levels marked on the graph. LOS A means smooth and fast movement. LOS C and D are moderate traffic conditions. And LOS F represents heavy congestion where vehicles move very slowly or stop and go. So the next one is base conditions and capacity. So these are the ideal conditions for analyzing highways. Lanes are 12 feet wide with 12 feet of lateral clearance. Only passengers cars are included, no direct access points, and it's divided highway on level terrain. Drivers are familiar with the road, and free flow speed is 60 miles per hour or higher. At level of service E, the volume to capacity ratio is 1.0, meaning the road is at full capacity. The next one is service measure. Both multi-lane highways and freeways use density as the service measure. That's the number of vehicles per mile per lane. It helps determine the level of service. For multi-lane highways, the density limit for LOSE changes with speed, but for LOSA to D, it's the same as freeways. So the next one is the free flow speed, or FFS. So free flow speed is the average speed under light traffic. It's estimated using the formula FFS equals BFFS minus FLW minus FLC minus FM minus FA. Age factor reduces the speed, lane width, lateral clearance, median type, and number of access points. In short, the more restrictions, the lower the FFS.
Good day everyone. Today I will be discussing the free flow speed adjustment factors. So, the lateral clearance adjustments. The adjustment is potentially restrictive. Lateral clearance FLC is determined first by computing the total lateral clearance, which is defined as TLC is equal to LCR plus LCN. So we have here the given formula. TLC is equal to LC sub R plus LC sub N, where TLC is the total lateral clearance in feet, and LC sub R naman ay ang total lateral clearance on the right sides. And for LC sub L is the literal clearance on the left sides. So as you can see from table 6.11, adjustment for literal clearance, it's shown how to solve the literal clearance adjustment for this formula. For median adjustments value for the adjustment factors for median types of FM are provided in the table 6.12. This table shows that undivided highways have a free flow speed that is 1.6 miles per hour, lower than divided highways, which include those with two-ways left-turn lines. Accordingly, for this table 6.1 adjustment for median types, it's reproduced with a permission for the transportations. For access frequency adjustment naman is the final adjustment factors in equation 6.7 is for the numbers of access point per miles. Accordingly, its access points are defined to include intersections and driveways on the right sides of the highways in the directions being considered that significantly influence traffic flow, and those do not generally include driveway to individuals' residences of services driveways at commercial sites. As you can see from table 6.13, for adjustment for access points frequency, it shows that the transportation for this problem solving are one of the common use for this access frequency adjustments.
Good day everyone. Today I'll be discussing examples 6.3, 6.4 and 6.5 from our lessons on multi-lane highways, capacity and level of service analysis. So these examples show how we estimate the free flow speed, determine the level of service and check how many trucks can be added before capacity is reached. So these examples involves a 4-lane undivided highway with 11 foot lanes and 4 pit shoulders on the right sides. So it has a 7 access points per mile and posted speed of 50 miles per hour. So our goal is to estimate the pre-flow speed. So we have these solutions. So we use these equations from the highway capacity manual. So FFS is equals to BFFS subtract by FLW minus FLC minus FM and minus FA. So if you don't know the BFFs and FFS, so BFFS is the base free flow speed and FLW is the lane width adjustment and FLC is the lateral clearance adjustment and FM is the median adjustment and last one is FA is the access point frequency adjustment. So going to solve this equation. So step 2 is to identify the adjustment values. So from the tables in our slides we have this given the 11 foot lanes, 4 feet shoulder and 7 access points per mile and the adjustment for undivided highways. So step 3 is to substitute all the given in from the table. So then we substitute all the adjustment values into the formulas. First is the VFS, which is given is 55 miles per hour and the 1.9 miles per hour of FLW and FLC is 0.4 miles per hour minus of the FM 1.6 miles per hour and FA is 1.75 miles per hour. So the results gives the estimated FFS for our given highway conditions. So last one is then we can compare our computed FFS with the posted speed. If the FFS is close to posted speed, it means driver can travel smoothly with much restrictions. So that's the example of 6.3. is 6.4. So in this example, the we analyze the 6-lane divided highway with 10-foot lanes, rolling terrain, and some heavy vehicles in the traffic mix. So the goal is to find the level of service or LOS. So step 1 is to compute the free flow speed, just like in example 3 6.3. We first calculate the free flow speeds and a 5-foot right shoulder and 2 axis point per mile. So step 2 is to convert the actual volume to passenger car equivalents, and next one is we adjust for heavy vehicles such as trucks, buses, and RVs. So we have to use the passenger car equivalence factors from the table. So this step converts the mixed traffic volume into passenger car units, since heavy vehicles move slower and take up more space. So step 3 is to compute the flow per lane, and after that we divide the directional volume by the number of lanes per directions, and we also apply the driver population factor given as 0.95 to adjust for non-familiar drivers. So step 4 is to compare the LOS criteria, and finally we compare the computed flow rate or density with the standard or LOS table for multi-lane highways. So its level from A to F represents the quality of traffic flow. So for example is the LOS means A means free flow conditions, while LOSF means heavy congestions. So step 5 is state the results. So by matching our computed values with the table, we can conclude the highway's current level of service, such as LOSC or D, and depending on the data. So that's all for the example 6.4. Last example is 6.5. Example 6.5. It's a multi-lane highway capacity. So the last example continues from example 6.4. So here we find how many large trucks can be added before the highway reaches its maximum capacity. So first step is use the capacity conditions. So we start from the service flow rate at capacity. Usually the flow rate at LOSE, we know the current passenger car equivalent flow from example 6.4. So step 2 is to add the trucks mathematically, and we add unknown number of trucks called X, and each truck is multiplied by its passenger car equivalent factor E raised to ATR. Then we set the total equal to the capacity of BPC 0 plus X times ATR equals to CPC. So step 3 is conclude. So this gives us a practical limit for truck traffic to maintain efficient operation on that highway. So here's the which gives us the 456, which is the number of trucks that can be added to the peak hour volume before capacity is reached. So in summary, these 3 examples shows the step-by-step process of evaluating highway performance. In example 6.3 focuses on speed, example 6.4 on service quality, and example 6.5 on capacity limits. So together, they help engineers and planners understand how different factors like lane width, shoulder width, and access points and truck volume affect highway performance. And that's all for my topic, and thank you for listening. So that ends our report.